Hey guys, this is a video on alternating series test. Before I get into the alternating series test, I want to do a little bit of review. If we have a series like this and we want to know if this series converges or diverges, this series right here, how do I figure that out? Well, I think about all of the tests that I have. For example, I always look at geometric series tests and I think, okay, is this a geometric series? If it is, then I just need to figure out my common ratio. So let's look at this. Is this a geometric series? If it were a geometric series, I'd have n equals 1, n equals 2, n equals 3, n equals 4. When I plug in, oops, sorry, this starts at 0. So I'm going to have to start actually at n equals 0. Okay, if I plug in n equals 0 right here, what I get is some number raised to 0 power, which is 1. If I plug in n equals 1, then what I'll have here is sine 2 over pi. If I plug in n equals 2, what I'll have is sine 2 over pi squared. If I plug in n equals 3, I'll have sine 2 over pi raised to the third power, and so on. Is this a geometric series? Is this a geometric series? Okay, well, let me see. When I move from one term to the other, do I multiply by the same r? Why, yes, I do. I multiply by sine 2 over pi each time. So therefore, this is a geometric series. What is my r? My r is equal to sine 2 over pi. Is my r equal to 1, less than 1, or greater than 1? Well, let's think about this. Sine 2, okay, is always between -1 or 1, okay? I mean, I don't know, actually, it is between -1 or 1. I don't actually know what number it is because it's not on the unit circle. But whatever it is, it's a number between -1 and 1. And pi is 3. So the biggest this number could be is 1. So what this tells me is that this number is actually less than 1. Okay, this is about 1/3, the biggest its number could be. And since it's less than 1, then I know that this series converges by geometric series test. All right, let's look at this series right here. Does this series converge or diverge? Well, I guess, is it a geometric series? So if I put in n equals 1, this is n equals 1, I'll get 1 over 1. If I put in n equals 2, I'll get 1 over the cube root of 2. If I put in n equals 3, I'll get 1 over the cube root of 3, and so on. So question, do I multiply by the same number each time, the same ratio each time to get the next term? No, that's not how this problem works. So this is not a geometric series. All right. The other tests I had were nth term test for divergence, which is not on this AP test, but it's worth looking at. Nth term test for divergence just says if I take the limit of this thing and I figure out that this number is not equal to 0, then this series will diverge. So if I take the limit of just this a sub n here, and if I do this, n gets bigger and bigger and bigger, this turns out to be 0, okay? If it's 0, then nth term test for divergence says, do another test, do another test. The nth term test for divergence does not work when you get a 0 for the answer. It only works if this number is not 0. All right, so the other test I know is the p-series test. So the p-series test has a certain format. It looks like 1 over n to some power, and I can rewrite this as n to the 1/3. This 1 doesn't have to be a 1, it could be a 2 or 3, it could be a number, and if it's a scalar, it would just pull out. So, but the most common way to say it is 1 is 1 here. All right, so if this is a p-series test, it does look like it matches the p-series test. Now be careful. If this had looked like this, okay, this would not be a p-series test. This would actually be a geometric series because this would be 1/3 plus 1/9 plus 1 over 27 plus 1 over 81. and so on. So just be careful with this one. A p-series test has n raised to a power. A geometric series has a number raised to n, okay? And this isn't always a geometric series just because you have this sort of format, but in general, you can see that this is a geometric series. All right, so let's look at the p-series here. What I have is p is equal to 1/3, and 1/3 is less than 1, okay? So therefore, what I know is that this series diverges by p-series test, okay? This problem right here, you could go through all of the possibilities. Is it a geometric series? Actually, it's not. Does nth term test for divergence work? The limit as n goes to infinity, if you just take this sequence here, e to the n over en plus 1, that is actually equal to, well, these leading terms here are the same, have the same power. So the ratio of their coefficients is 1. And the nth term test for divergence says I compare this 1 to 0. It's not equal to 0. Therefore, I can use nth term test for divergence. This says that this series actually diverges by nth term test for divergence. And nth term test for divergence is not on the AP test, but it's worth looking at because it's actually good to know. It comes up again and again on things that we're trying to find the convergence and divergence of a series. Let's look at a clarification for p-series tests. I want to just make sure you guys understand that when you put a plus 2 here, when I have the sum of 1 over n cubed, this actually converges by p-series test because your p is equal to 3, which is greater than 1. All right, but if you put a plus 2 here, this no longer can use the p-series test. Okay, this one actually needs to use the DCT or LCT test, and I talked about that in a previous video, but I wanted to clarify that while if you add a 2, you can no longer use a p-series test. If you multiply by 2, okay, this still is a p-series test. Okay, multiplying by 2 doesn't change the ability to use a p-series. The reason is because you could actually factor out a 2. The series here acts a lot like an integral sign, so you can factor out the 2 because the 2 is a scalar. And if this thing out here converged, then just because you multiplied it by 2, it wouldn't change the convergence or divergence of this series. All right, so it's okay to multiply by 2. It's also okay to multiply by 1/2. Okay, and this also, you could use the p-series test for this sort of problem. And then I've talked about this before, but if you had a problem like 1 over 3 to the n, okay, this is not a p-series because p-series is n raised to a power. If you have a number raised to a power, this is likely a geometric series, and you should test it to make sure it is. All right, let's go ahead and look at your formula sheet, the last 2 pages of your formula sheet right now. On this page of your formula sheet, this will not be covered anymore on your AP exam. These polar things are not going to be covered. These 2 things will be covered, and the Lagrange error bound will no longer be covered on the AP exam for 2020. The alternating series remainder, I told you to circle the bottom part, but actually, re-looking at everything, none of this is covered. The reason is this right here. If you look at what AP says, College Board says will be on the AP exam, determining absolute and conditional convergence is not on the AP exam. It's 10.9, and that's what this part down here is, determining absolute and conditional convergence. But I'm going to talk about it in this video anyway, and I'll tell you, when we get to that point, I'll tell you when you can stop listening if you don't want to know. But I wanted to make sure you understood that it won't be on the AP exam this year. All right, let's look at the last page of your formula sheet. Nth term test for divergence is not going to be on the AP exam this year. geometric series will be, telescoping never is, P-series will be on the AP exam, alternating series will be on the AP exam, but this remainder part will no longer be on the AP exam for 2020. If we scroll down, the integral test will not be on the AP exam, but basically what the integral test is just saying, hey, if you have a series, if you take the integral of that from whatever these same numbers are, 1 to infinity, if the integral converges, then the series will also converge. If the integral diverges, then the series will also diverge. They walk hand in hand. But again, the integral test will not be on the AP exam this year. Ratio test will be. The root test has never been on the AP exam, and the direct comparison and limit comparison test won't be, and that was on a previous video if you were curious about that. Alright guys, let's look at the notes for alternating series for convergence, okay? And again, this is a convergence test. It's not a divergence test, so there's no way to tell if a series diverges with this test, but it does tell you if the series converges. First of all, let's look at what an alternating series is. An alternating series is a series whose terms alternate from positive to negative or negative to positive, all right? And the key there is this expression right here. This expression, when you plug in 1, and then you plug in 2, and then you plug in 3, it will make this series alternate from negative to positive, okay? And this expression also will do the same thing, okay? And something else you might want to just take note of, this expression here is equal to the sum of n equals 1 to infinity of cosine n pi times 1 over n factorial. So this part here, this also causes a positive negative change, okay? And you can look at that. If you think about the cosine, cosine pi is over here, cosine 2 pi is over here, so cosine pi is going to give you -1, cosine 2 pi is going to give you +1, cosine 3 pi is going to give you -1, and such. So anyway, these things that are circled here, these 3 things that are circled all help you to figure out that this is an alternating series. All right. Then you have this extra part here. Okay. These extra parts we're going to call your a sub n's. Okay. So we're going to call this your a sub n, and this your a sub n, and this your a sub n. And different books label these things different ways. So this is just how we're going to do it. Okay. And we talked about before that if you took the limit of your a sub n and you got 0, you couldn't, it didn't tell you anything, okay? If you didn't get 0, then the nth term test for divergence told you that this series would diverge, okay? But if you get 0, you cannot use the nth term test for divergence. You have to use another test, all right? Now, the alternating series test is kind of interesting because the alternating series test says that actually this is useful if you have an alternating series. All right, so let's talk about the alternating series test. The alternating series test says that if you have a series, okay, that alternates, okay, so it alternates in signs, okay, then if the limit of your a sub n goes to 0, okay, and your terms decrease in magnitude, so each subsequent term gets smaller and smaller and smaller, then what you know is that the series converges, okay? So what 3 things have to happen for the alternating series test to be used? First, your terms have to alternate in sign. Second, your terms have to have a limit of 0, so that means a limit as n goes to infinity of your a sub n must equal to 0. And third, your terms must decrease in magnitude, so that means, and we're just looking at magnitude, so that means each subsequent term must be smaller than the term before it, okay? All right, so make sure you understand that if you do get this right here, this second condition here, if you do figure it out that it's not equal to 0, then you cannot use this alternating series convergence test. Okay, if you figure out that the limit of a sub n is not equal to 0, then what that means is that your series is going to diverge by the nth-term test for divergence, okay, not by the alternating series test. Why? Because alternating series test is only a convergence test. It will never tell you about divergence, okay? Let's look at some examples. So right here, this says determine whether the following series converges or diverges. All right, so what we're going to see is that this is an alternating series. Why? Because this term here causes the series, the sequence to go -1, +1, -1, +1. All right. So what we say is we say one, well, I'll say the terms 1 alternate. Okay. Then I check to see if the limit of this thing goes to 0. So what I do is the limit as n goes to infinity of this, whatever's left, this a sub n. So this right here is called your a sub n. N over 2n minus 1. Does it go to 0? Let me see. This is equal to, well, here's your leading terms here. So this is actually equal to the ratio of the coefficients of the leading terms, which is 1/2. Well, this is not equal to 0. All right, so let's look up here. In order to use the alternating series test, this limit must be equal to 0. Well, I have this limit is not equal to 0. So I stop right there. This series diverges because of the nth term test for divergence. Okay, so this series here actually diverges. Okay, and some of you guys might say, wait, hold on a minute, what about the alternating part of this? Well, if you think about it, if this were negative 2n minus 1, then you get -1/2 here, and therefore this would not be equal to 0. And if we're positive, okay, you would get +1/2 here, and this would not equal to 0. So either way, you would get something that diverges by nth-term test for divergence. And that's why we don't have to worry about if it's positive or negative for nth-term test for divergence. All right, so alternating series test was not used here. Let's look at letter B here. All right, letter B says you've got an alternating series. So let's start with this. The terms 1, they do alternate. Okay, the second thing I need to look at is, do the terms have a limit of 0? All right, so let's look at this. This would be the limit as n goes to infinity of the a sub n. So whatever's left here, right here, this is your a sub n. Be careful, there's a 1 on top here. So this is 1 over n squared. All right, does that equal 0? As n gets bigger and bigger and bigger, this does equal to 0. Okay, so therefore I'm good so far with the requirements of the alternating series test. Now I need to see if third, the terms decrease in magnitude. So let's think about these terms. Okay, do they decrease in magnitude? Decrease in magnitude. Well, if I put in, okay, now I only need to look at the absolute value, so I need to just look at this a sub n. If I put in 1, I'll get 1 over 1 squared. If I put in 2, I'll get 1 over 2 squared. If I put in 3, I'll get 1 over 3 squared. Are these terms decreasing in magnitude as n goes to infinity? Yes, they are. So check, they are decreasing in magnitude. All these are checks, so therefore the series will converge by alternating series test. All right, so this series right here converges. Let's look at this alternating series here. Let's verify first that it's alternating right there. Okay, so since the terms 1 alternate, okay, we're going to check to see if the alternating series test works on this. Check. All these 3 conditions must apply. Let's look at the second condition. The second condition says we must have a limit of 0. All right, so let's go to the second condition. The limit as n goes to infinity of n over ln of 2n. What is that? Well, if I plug in infinity, what I'll get is infinity over infinity. And what does that mean I can do? I can do L'Hopital's. What does this L stand for in L'Hopital's? This L stands for limit, so this is a limit as n goes to infinity of the derivative of the numerator, which is 1, over the derivative of the denominator. Okay, remember, the derivative of ln of u is equal to u prime over u. So this is going to be 2 over 2n, and that's going to be equal to the limit as n goes to infinity of, this is really 1 over 1, right? So of n, and if you plug in infinity here, what you get is infinity, and infinity is not equal to 0, right? So what we wanted was for this to have a limit of 0. The limit is not equal to 0, so what we know is that this series actually diverges by nth-term test for divergence. All right, so this series here actually diverges. Another way you could have gotten infinity here, I don't know if you saw it, was this is n over ln of 2n, and n, if you graph this, and ln of 2n is, if you graph it, the n is going to approach infinity a lot faster than the ln of 2n. So therefore, what you actually have here is big over small. And that's another way you could have said, well, you know that this is d and e, and d and e is not equal to 0. One thing I want to talk to you about is these two conditions up here have a limit of 0 and decrease in magnitude. Sometimes students wonder, aren't these always the same thing? Well, most of the time they are. Most of the time, if 2 is true, then 3 is also true, but not all of the time. So what I did was I put inside your notes an explanation of when the limit of 0 and decreasing are not exactly the same things. And this isn't something that the AP test is going to trick you on. Most of the time they're going to mean the same thing, so you don't really have to distinguish when they're different. But there are situations when they don't exactly mean the same thing. And in your notes, if you look through this, it'll explain to you why sometimes these are not necessarily the same thing. All right, let's look at your homework. Your homework on the 2020 AP exam, you have problems 1 and problems 4 through 6. Okay, I left the ones that will not be on the AP exam, but I left them here for those of you guys who want to continue with this video and follow along and learn about nth-term test for divergence and absolute or conditional convergence. Those of you guys who are good with just learning the minimum amount that you need to know for the AP exam, you can turn off the video at this time. And so, again, this is not on the AP exam. I'm determining absolute or conditional convergence in an alternating series. Let's look at what this says. This says that if you go and you figure out that it's an alternating series and it converges, which we've already learned how to do, okay? This says those 3 things. 1, the terms alternate. 2, the terms have a limit of 0. And 3, the terms decrease in magnitude. Okay, if all these things are true, we've figured out that the alternating series converges. All right, once you figure that out, then if you ignore this part here and you just take the series of your a sub n, if that converges, then what you will say is that your series absolutely converges. If you ignore your alternating part here, okay, and you figure out that, well, first of all, you have to say that the series converges by alternating series test, all right? But if you ignore your negative 1 over n here, the alternating part, and you figure out that your a sub n actually diverges, then what we say is that our series is conditionally convergent. All right, so let's look at some examples of that. The first example here, letter A, says, okay, let's figure out if this alternating series converges or diverges. So first it has to be an alternating series, all right? So let's look at the conditions there. First, the terms alternate, check, because of this thing right here. 2, does the limit of your a sub n equal to 0? So the limit as n goes to infinity of what's your a sub n here? It's really 1 over the square root of n. Okay, well, does this equal 0 or not? Well, the bottom gets bigger and bigger and bigger. The top holds at 1, so yes, this is 0. So far I'm good on my conditions for an alternating series test converging. And the third thing I need to look at is, do these terms decrease in magnitude? So 3, do the terms decrease in magnitude? So if I look at that, what I see is I'll have 1 over the square root of 1, and then 1 over the square root of 2, then 1 over the square root of 3, then 1 over the square root of 4. Are these terms decreasing in magnitude? Check. So I have 3 checks here. Okay, so what I say is, therefore, this series, this series right here, well, I guess, I don't know if I should say the a sub n, but this series converges by alternating series test. Okay, this series does converge. All right, then my question is, once I know it converges by alternating series test, does it converge absolutely, or does it converge conditionally? And the way I figure that out is I go to this a sub n. I just look at the a sub n only, and I make that a problem by itself. So this 1 over this series of 1 over square root of n. And we haven't looked at that yet. We did look at the limit of this, okay, but that's not the same as looking at the series of this. Now, the limit of this right here goes to 0, but the series here, okay, I know from the p series test that this p is equal to 1/2, okay? So therefore, this series here, okay, is going to diverge by the p series test, because this 1/2 is less than 1, all right? So if this series diverges, so here we go, if this series diverges, but the original alternating series converge, then what I know is that this series right here, we say, is conditionally convergent. All right, let's look at this problem right here. Okay, we're going to do a similar thing. Okay, first we have to figure out, does this alternating series converge? So let's look at the conditions. Okay, number 1, do the terms alternate? So let me write this word first. The terms, 1, they do alternate because of this negative 1 over n, check. 2, does the limit as n goes to infinity of the a sub n, so the a sub n is here, of 1 over 3n, does it go to 0? Yeah, as n gets bigger and bigger and bigger, the denominator gets bigger and bigger, so yes, it goes to 0, check. Third, do the terms decrease in magnitude? So let me look at the terms. Now I'm just looking at the magnitude, so I'm just looking at the a sub n. I'll have 1 over 3 to the 1, 1 over 3 squared, 1 over 3 third, 1 over 3 4. Do these numbers decrease in magnitude? Yes, they do. So this series converges. It converges by the alternating series test. Now, once we know that a series converges by an alternating series test, if we ignore this alternating part, if the a sub n converges, we can find out if the series converges absolutely or if the series converges conditionally. So what we do here is we take this series of just the a sub n. So the a sub n here is 1 over 3n, and we figure out, does this series converge or diverge? And it might feel like we've already done this, but we haven't. We had figured out if the limit went to 0 or not, but we did not figure out if the series converged or diverged. If we examine this carefully, we can tell that this is actually a geometric series. The r here is 1/3. 1/3 is less than 1, so therefore we know that this series here converges by geometric series test. So if this series here, this sum of a sub n, converges, then what we know is that the original series was absolutely convergent. So we can come down here and write absolutely converges. So this series right here, the original series we had, was absolutely convergent. All right, some of you guys might be asking, all right, what's the difference between conditionally convergent and absolutely convergent? What does it really mean? And so while you don't really need to know what it means for the AP exam, there's an explanation here to help you understand what it means. And it basically says that if you have a finite sum, which we're used to having, you can rearrange these numbers and you'll get the same sum. But when you have an infinite sum, that is not necessarily the same. The same rules don't apply, that you can rearrange it and you'll get the same sum. If the series is absolutely convergent, then when you rearrange these terms, you'll get the same sum. But if the series is conditionally convergent, like this series is here, then when you rearrange, you can rearrange these terms in order to get a completely different sum, which is funky but true.